Have you ever stopped to think about the code that runs pretty much everything in our lives? When you look at it, you see syntax, logic, a bunch of rules. But what if all of that? What if the very structure of our programming languages wasn't just something we humans invented? What if it's actually echoing something much, much deeper? A kind of cosmic code that's been hiding in plain sight this whole time.
So let's ask the big question right up front. Are the languages we use to build our digital world just arbitrary? Just a bunch of conventions we all agreed to follow? Or did we accidentally stumble upon something fundamental, something that would be true for any intelligence anywhere in the cosmos?
History is full of these incredible moments where two totally separate fields just crash into each other and create something brand new. Think about it. Geometry and algebra? Boom, you get coordinates. Particles and waves? You get quantum theory. Well, we're about to explore a connection that's just as massive, the mind-blowing link between pure abstract logic and the nitty-gritty of computation.
To really get this, we've got to go back in time and follow two different stories that started out completely separate, like two rivers flowing towards some unknown ocean. Our first river, well, it begins in the early 20th century with a bunch of logicians on an incredibly ambitious quest to build a perfect, unbreakable foundation for all of mathematics.
So picture it, the early 1900s. A brilliant mathematician, David Hilbert, launches this grand project to basically turn all of math into a formal game of symbols. His ultimate goal? To solve what he called the entscheidungs problem, or the decision problem, basically creating a machine that could tell you if any mathematical statement was true or false. The optimism was just off the charts. And right in the middle of all this excitement, this guy Gerhard Gentzen comes along and invents a totally new way to think about proof.
This quote from Hilbert just says it all. We must know, we will know. It's a statement of such incredible confidence, of absolute certainty. It was even engraved on his tombstone. The beautiful irony, of course, is that Kurt Gödel had already proven this grand dream was impossible. But the quest itself, well, it led to something amazing.
And here's the core of what Gentzen figured out. It's so elegant. He saw that logical rules should always come in these neat little pairs. For any logical idea like and, there's an introduction rule that tells you how to build it and a matching elimination rule that tells you how to use it. This idea of perfect symmetry turns out to be absolutely key.
Okay, let's put a pin in that for a second and jump over to our second river. Because while the logicians were busy trying to perfect proofs, a totally different group of thinkers was wrestling with another question, one that sounds simple but is incredibly deep. What does it actually mean to compute something? What even is an algorithm?
And this is one of my favorite little bits of history. People have been using algorithms for thousands of years, right? But nobody had a solid formal definition. Then you get to the 1930s, and you know the saying about waiting for a bus? 3 different definitions came along at almost exactly the same time.
So let's look at two of the giants here, Alonzo Church and Alan Turing. They came at this problem from completely different angles. Church, a pure mathematician, came up with this abstract system called lambda calculus and basically said, this is it. This is computation. Turing, on the other hand, did something different. He thought about what a person, a human computer, actually does with a pencil and paper, and he built his famous machine model from that. And it was Turing's down-to-earth, philosophical argument that convinced everybody, even the skeptics, that they'd all arrived at the same fundamental idea.
But, and this is a huge but, there was a problem. Church's first version of his system was broken. It had a paradox, a fatal flaw. So to fix it, he came up with an idea to classify all the terms in his system into different types. At the time, it probably felt like a patch, just a necessary bug fix. He had no idea he had just stumbled upon the missing piece of a puzzle he didn't even know he was solving. And this is it. This is the moment. Our two rivers, the quest for perfect proof and the race to define computation, which had been flowing in parallel for decades, they're about to merge. The people in these two fields thought they had nothing to do with each other. They couldn't have been more wrong.
The discovery is known as propositions as types, or sometimes the Curry-Howard isomorphism. And what's so wild is that it apparently started as a curiosity, almost a little pun that logicians noticed, but it turned out to be this incredibly deep one-to-one mapping. It says that mathematical propositions and computer data types aren't just similar, they are structurally the exact same thing.
And this connection isn't just on the surface, it goes all the way down. There are 3 perfect layers to this mirror image. A proposition in logic, a statement that can be true or false, maps perfectly to a type in a program. A proof of that proposition? That's a program. And the process of making a proof simpler and more direct? That is literally the same thing as running the program.
Okay, let's make that super concrete. Take the logical word and.
If you want to prove the statement A and B, what do you need? Well, you need a proof of A and you need a proof of B, right? In programming, what's a thing that holds an A and a B? It's a pair or a struct. It's the same thing. Or how about if A, then B? A proof for that is a method that can take any proof of A and turn it into a proof of B. What does that sound like? It's a function. It takes an A as input and gives you a B as output. It is a perfect, stunning match.
All right, that's a really beautiful, abstract idea. But you're probably thinking, so what? Who cares? How does this ivory tower discovery actually affect the real world? Well, the answer completely changed how we build reliable software.
This principle is literally the bedrock for some of the most powerful and safe programming languages ever designed. We're talking about languages like ML, Haskell, F#, Scala, and even these incredible tools called proof assistants like Coq and Agda, which are built entirely on this idea.
And the result is a totally new level of confidence in our code. We can now build software that isn't just tested for bugs, but is mathematically proven to be correct. For instance, using these very principles, engineers have formally verified 20,000 lines of code for a browser plugin. That code is guaranteed to work as specified.
And maybe the most mind-blowing example is something called compcert. It's a compiler for the C programming language. But here's the thing. The compiler itself has been formally verified. This means the tool that turns your source code into a runnable program is mathematically proven not to introduce any bugs in the process. The level of reliability that gives you is it's incredible.
So, this all leads to a final, pretty cosmic question. If this connection between logic and code is so perfect and so powerful, where did it come from? Is it a clever pattern that we invented? Or is it a fundamental feature of reality that we just discovered?
To think about that, just look at the plaque they put on the Pioneer spacecraft. It was our message in a bottle, flung out into the cosmos. And they had to put things on it that they thought any intelligent species could figure out, like the position of our sun relative to pulsars, or the structure of a hydrogen atom. They were trying to speak in the language of the universe.
Now, let's apply that idea to code. If we sent an alien civilization a C program, that would be like the drawing of the humans on the plaque. It's just our local custom. They'd have no idea what to make of it. But what if we sent them a program written in typed lambda calculus? The whole propositions as types idea suggests that would be like sending them the pulsar map. It's based on pure logic, a language that any thinking creature would eventually have to discover.
The computer scientist Philip Wadler puts it perfectly with this quote. He says, look, you can imagine a universe with different laws of physics, right? Where gravity works backwards. But can you even begin to imagine a universe where the rules of logic don't apply, where a thing can be both true and false at the same time? It's just inconceivable.
And that brings us to our final, lingering thought. If this language of logic and computation isn't just true on Earth, but would be true and discoverable in any possible universe, then is calling it a universal language even doing it justice? Maybe. Maybe that word is just too small.